Hello and welcome to my science education presentation on the synthesis and characterization of gold nanoparticles. My name is Matthias Carroll. I'm a graduate student at Central Washington University and a part of the Lohse research group where we investigate gold nanoparticles. To begin with, what is a nanoparticle? A nanoparticle is anything that has one side less than 100 nanometers in length. Americans may not be all too familiar with a meter, but as teachers you should know what a yardstick is. A yardstick is 3 feet. A meter is 100 centimeters, just slightly larger than a yard. And another thing that might be a good reference for you is that a full-size acoustic guitar is about 1 meter in height. So to put this in a perspective, a nanometer is to the meter stick what the diameter of a penny is to the diameter of the Earth. I work with gold nanoparticles, abbreviated AUNPs, because the elemental symbol AU stands for gold, and these are about 5 nanometers in diameter, equivalent to just a few pennies lined up compared to the entire diameter of the Earth. Why are nanoparticles important and why are they of interest? Nanoparticles are important area of research because their optical and electrical properties deviate from that of the bulk material. As things get smaller, we're noticing that they interact with matter and energy in different ways. Nanoparticles are renowned for their catalytic activity. They lower the activation energy of otherwise unfavorable reactions, and so they have many uses as catalysts, mainly like a catalytic converter that's platinum on a ceramic bed that is inside your car's tailpipe, and it takes exhaust and helps fully oxidize it, so it's better for the environment, more beneficial. One of the reasons why nanoparticles are superior catalysts is that they have a higher surface area to volume ratio. For example, on the left is a 1 troy ounce bar of gold. I did the math and it's about 0.29%, or about a third of a percent, of all the atoms are on the surface. Those are the atoms that are available for reaction. The interior atoms are not beneficial as far as catalyst is concerned. Conversely, a spherical nanoparticle that's about 5 nanometers in diameter, over 17% of the mass of those atoms are on the surface, so it's about 50 times more energetic or more favorable. On the bottom right here I have the Minecraft representation of a gold nanoparticle, similar to something like a basketball. If you hold it at arm's length, it looks spherical, but the closer you bring it in, the more you magnify, you see that there is topography, there are bumps on the surface. So a gold forms in FCC, face-centered cubic lattice structure, the smallest building blocks, like our Minecraft analogy. So when we get to something that is nanometers in size, the surface topography doesn't look perfectly smooth. It looks more jagged, like this Minecraft representation here. And so these vertices, those edges, are very reactive for these actions. So gold's been known since ancient times. Previously it was very difficult to separate from other precious metals such as silver because they have very similar chemical reactivity. In fact, a lot of modern counterfeits of old coins, they find out because the modern counterfeits are very pure, whereas in the old days it was very difficult to separate silver and gold. So here's an example of AUNPs, that is gold nanoparticles, in ancient Rome. This is the Lycurgus cup. It is an artifact thought to be around 300 AD, and it displays one of the properties of gold nanoparticles. It's called anisotropy. Anisotropy is a generalized term that means that the properties are different depending on the perspective that you look at. So the reflected light versus the absorbed light, the light that's shown through versus reflected back. Here we see that gold nanoparticles absorb light in the 520 nanometer wavelength, that is green. So because they absorb the green, they appear red because they reflect red light. So there's a variety of ways to synthesize gold nanoparticles, right? Technically you could do it through mechanical breakdown, right, if you were just beating at a piece of gold. However, you wouldn't have very much control over the size of the material. You might get some nanoparticles, but the sizes in general would be erratic. So we do this instead of from the top down, from the bottom up. We convert soluble gold ions into the metallic gold nanoparticles through reduction, that is the gaining of electrons, and after that we protect them from the environment with a ligand that is a surrounding molecule. That way that these newly formed gold crystals don't bump into each other, aggregate, and form larger and larger particles. We want to stop that particle growth from happening at a particular point. So similar to the sodium chloride table salt in your water is not the same as sodium metal, right? This Au3+, that is gold 3 ion, is fundamentally different from metallic gold, Au to the 0 or Au0, that is the metallic ground state of gold. So how do we synthesize these? For beginning, we start with ultra-pure gold, and then we use a powerful oxidizing acid called aqua regia. It's a combination of nitric and hydrochloric acid, and it is one of the few things that is able to dissolve gold, and it forms this chloroauric acid. Basically, gold 3+ is surrounded by chlorine, that's the ligand, to protect it. Aqua regia, the name actually roughly translates to the king's water, because gold was a noble metal, and the king is the noble. It was this noble water, which is one of the few solutions that are able to dissolve gold. Our second major component is sodium borohydride, probably known as the trade name borax, and it serves as the electron donor, that is the reducing agent, and to form metallic gold. We passivate ours in my research lab with a ligand called MPTMA. I'll show you the structure here on this next slide. MPTMA is a little bit of a mouthful. It stands for mercaptopentane trimethylammonium chloride. Mercapto is an anachronistic term for a thiol group, this SH. It's an analog, same as alcohol OH, but the sulfur is right below oxygen in the periodic table. And then the pentane, we've got 5 carbons. Our nitrogen here, that's the ammonium. Trimethyl, we have 3 methyl groups, and it is a salt. Nitrogen typically has 5 valence electrons, but because we only have 4 bonds to it, it's really only getting 4 electrons, so it has a positive charge. The chlorine has a negative charge, so that when this dissolves in water, it dissolves very well. So here's the experiment that is most recent we've been running. We're trying to affect the core diameter size by means of controlling the pH of both our 2 major reagents. We have our gold reagent, chloroauric acid, and our reducing agent, borohydride. The total base added, for our base we're using sodium hydroxide, is consistent throughout all the measurements, but we're altering the amount of that's in the gold versus the borohydride reagent. Alright, here's some photos. On the left here, you can see that this yellow color, it looks like urine if you're dehydrated, severely dehydrated. It's not much to look at here. This is our gold, our chloroauric acid. The reason why there's not much to show you is that because it's expensive, we synthesize it in small amounts. Secondly, it can undergo some photo decomposition where the light will reduce it back to metallic gold, and that's not wanted. So we wrap this up in tin foil. We try not to synthesize more than we need at any one time. We use these 50 milliliter centrifuge tubes as our reaction vessels, and these stir bars in the middle here, those have just come out of a reaction. They have small bits of gold plated onto them. It doesn't look like gold as you would imagine it in jewelry. It's not that nice orange rich color because it is so small and it's not uniform. It's not nice and smooth like a mirror. It looks dramatically different. Versus on the right, these are these stuff here. It's a Teflon coated stir bar where it's a magnet surrounded by Teflon, which is very inert chemically. And here's them looking blast white after we've cleaned them. In order to clean them, we take these 2 carboys of acid. We have nitric acid and hydrochloric acid. They're quite concentrated, and we mix them together to form aqua regia, and that is this angry orange beaker on the bottom left. It releases some toxic fumes, some what they call NOx, where it's nitrogen oxides, and so we do this in a fume hood. We have an abundance of safety that we take into account. For example, we use 2 different gloves. We double up on the gloves, etc. And then we rinse these multiple times and put it in the waste jar because it releases like chlorine gas, among other things. So on the right, we see this gradient. It's a little easier to see in person, but the left has the least amount of sodium hydroxide base added to the gold, and then increasing amount makes the solution more colorless. So let's talk about the phenomena associated with nanoscale particles. These particles are so small that they are about the same size or on the same scale as visible light. Visible light goes from 400 to 900 nanometers approximately. Due to their size, we observe this phenomena called surface plasmon resonance, and we'll abbreviate that SPR. I like to describe this as similar to an opera singer's voice when they can hit a very high pitch and like shake a wine glass, right? They are imparting mechanical energy from their voice as it travels sound waves. At a characteristic frequency, light is absorbed, not reflected, by a gold nanoparticle. We use an instrument called a spectrophotometer to shine full spectrum visible light through these solutions and observe where these plasmon absorbance signatures are. This characteristic absorbance peak, called the plasmon, is used to determine the size as well as the homogeneity of our particles in solution. And similar to a tuning fork, the size of our particle changes where this plasmon is. So with the tuning fork you have two tines, and depending on the band gap between them, the standing wave corresponds to different frequencies, different pitches. For example, if we take a gold nanoparticle and functionalize it with an antibody that corresponds to a specific protein, when this antigen, in this case a protein, has bound to this gold nanoparticle functionalized with an antibody, the absorbance, the plasmon, is redshifted. So it's shifted to a longer wavelength, lower energy light. We call this redshifted because it goes more towards red. That's the lower energy light. Here are some more photos. On the left here is indicative of a successful run. Again, it looks a little better in person, but it's like a wine red. When it's concentrated, when we dilute it, it's more like a pink Moscato sort of look. Versus in the center, this is an example of what would be a dead or a not successful synthesis. So we use a microchannel cuvette. That's what this glass square is. It's like a rectangle. It's black on the inside to minimize internal reflection. We want light going straight through it, not bouncing around. And if you can see here on the top where the triangle is, there's a little bit of like purplish haze. That's actually gold that's been plating onto the glass. And so we clean these periodically with aqua regia as well. On the right, this mauve color is an example of dilute gold. After we run a batch through this cuvette, the spectrophotometer, we dump it out, rinse it 3 times, fill it up with new solution, and so this dilute color is a nice sort of mauve. It should be noted as well that the environmental fates of gold nanoparticles aren't fully known, whether they bioaccumulate in animals and humans, so we take great precautions to dispose of these responsibly. We keep track of every milliliter in special carboys that get disposed of. So here's what a typical run would look like. On the right we have this little compass rose that tells you that black is our first trial, the black line, and the red, blue, and teal, in order of increasing base added to the gold. And it's hard to see, but the maximum absorbance peak moves slightly to the right, that is redshifted, as we go along this trend, from black to red to blue to teal. And this is what we're expected to find, is that the particles get larger the more sodium hydroxide we are adding to the gold. I mentioned earlier that the homogeneity of the solutions can be determined just with this UV visible spectra. If you look at the royal blue color, it's a very sharp, narrowly defined absorbance, right? Like the standard deviation is small, versus the teal color, it's more broad and diffuse. So the blue would be an example of a successful synthesis where all the particles are very similar in size and shape, versus the teal color is not as effective. So how do we process our data? We use empirical findings from other nanoparticle research groups, namely Lohse et al., to get a good estimate of our particle size. They have working curves that they've established through known sizes, and we can relate our findings to those. Eventually, we seek to image our particles with X-ray diffraction and electron microscopy. So we mentioned that nanoparticles are about the size of light rays, 400 to 900 nanometers for visible light, whereas X-rays are more energetic than visible light, so their wavelength is even smaller. So as a general rule, the smaller you use, the smaller your ruler, or the smaller your graduations, the more accurate you're going to have a measurement. Say, for example, on a macroscopic scale, if you're trying to measure the length of your house and your ruler is a school bus, you'll get maybe a fraction of a school bus, or one and a fraction of a school bus. You won't really have a very well-defined picture, versus if you're using something smaller like a car down to a refrigerator or to a microwave, you're going to have still a fraction left over, like 15 and a half microwaves, but because your microwave is even smaller than your school bus, you're going to have a more constrained picture, higher resolution, more accurate reading of the size. On the bottom here I have an example of one of our trial runs. We have our 4 different amounts of sodium hydroxide added to our gold solution, our characteristic surface plasmon resonance peak, that's lambda max as a wavelength, and there's a general trend that our wavelength is redshifted as the particles get larger as we increase the sodium hydroxide concentration in gold. And it's about 3 to 5 nanometers consistently. Here I show some statistically significant results. These are after 3 trials. As you can see, we do indeed have an increase in the SPR wavelength, that characteristic peak, as we increase the amount of base in our solution. However, there is an inflection point when we look at our size. We have an increasing size, and there's an inflection point where 500 microliters of sodium hydroxide actually corresponds to a decrease in particle diameter. And this is unknown why this mechanism is happening. So it's something we're going to investigate. I want to leave you with a quote from one of my shows that I like, Mythbusters. One of the scientists on there is attributed to having said, "The only difference between screwing around in science is writing it down." And that is something that I have definitely learned from as a graduate student who's doing research, is that things don't always go as according to plan, and so I need to be dutiful in recording everything that I observe. For example, at the beginning of this quarter, when we were doing our reactions, I noticed in one reaction that for a time this orange precipitated form. And at first I chalked this up to, it was a fluke, it was an error. Maybe there was an impurity, or my stir bar wasn't clean enough. I consulted my professor, and he said, well, our MPTMA, it's a chloride salt, but it actually comes from the ion displacement of a bromine salt. So maybe that's free bromine. Bromine is like a reddish liquid, but in dilute, it could be like an orange. So we had thought that, but with successive attempts, we'd done this multiple times, and we consistently got this orange. So we ended up reversing the order of addition, and that ceased to be a problem. We think that it's in fact a gold 3 hydroxide, and it bears a similar resemblance. Thank you very much for watching my presentation. I'd like to extend a thank you to the Lohse Research Group, Dr. Tim Sore, my science communication professors, Dr. Ann Egger and Dr. Nicholas Temple, and ultimately thank you very much for watching my presentation. Please leave your questions in the comments below. And one last thing, I should mention the 3 photos I got from the internet. Thank you very much.